Hello. In the previous chapter, we were doing the effect of intensity and the potential on photoelectric current. In this lecture, we will see the effect of the other variables on the photoelectric current and the laws of photoelectric effect, Einstein's photoelectric equation. Now, what is the effect of the frequency of the incident light on a photoelectric current? When a graph is plotted for the frequency of the incident light, then the shape is like this, and it has been observed that with the increase in the frequency, there is no change in the photoelectric current. Photoelectric current is same, that is the saturation value of the current is same whatever be the frequency of the incident light. It means the photoelectric current is independent of the frequency of the incident light, or you can say the energy of the photons. Now, let us see the effect of the frequency on the stopping potential. Now see, with the increase in the frequency, the value of the stopping potential increases. It becomes more and more negative. It means the value of the stopping potential increases with the increase in the frequency. It means it depends on the energy of the photons. Now the question is, what is the stopping potential? I told the stopping potential in the previous lecture. Now I repeat it. Stopping potential is the negative potential of the anode at which the photoelectric current becomes zero. This is the stopping potential for the frequency nu2. This is the stopping potential for frequency nu1. For this graph, the energy of the photoelectron is more than this one. Threshold frequency. When a graph is plotted between the stopping potential and the frequency of the incident light, then it will be a straight line, but it never passes through the origin. It means there is no emission of the photoelectrons if the frequency is below some minimum value, and that minimum value of frequency is called threshold frequency. The value of the threshold frequency is different for the different material. The threshold frequency depends on the work function of the metal. Work function of the metal is the property of the metal, and it is the energy required by a metal to give out the electron. The minimum energy required is the work function of the metal, and the work function of the different metal is different. That is, the work function of the metal is given as h nu, where nu naught is the threshold frequency. On the basis of this study, it is concluded that there is a minimum value of the frequency called threshold frequency, below which no photoelectric emission is possible, however large the intensity of the light is. The second, the number of photoelectrons emitted, that is the photoelectric current, is directly proportional to the intensity of the light, however, whatever be the frequency. Okay, but it should be more than the threshold frequency. The maximum kinetic energy of the photoelectron is directly proportional to the frequency, provided frequency should be more than the threshold frequency. And it is also observed that the maximum kinetic energy of the electron is independent of the intensity of the incident light. The process of the photoelectric effect is instantaneous, means as the light is incident on the substance, it gives out electrons immediately. On the basis of these laws and the experimental studies, Einstein develops the photoelectric equation. Say it is some metal and the light ray is incident on this metal. That is the photon whose energy is equal to h nu is incident. This energy is used in two ways. It is absorbed by the metal, and the energy absorbed by the metal is equal to the work function of metal, and rest of the energy is given to the electron in the form of its kinetic energy. So the energy of the photon is equal to the work function of the metal and the kinetic energy of the electron. Phi is the work function of the metal, h nu is the energy of the photon. As already I told you, work function is equal to h nu naught, where nu naught is a threshold frequency. So the kinetic energy of the electron can be written in this way. Right? This equation is Einstein's photoelectric equation. Nu naught is a threshold frequency. No photoelectric emission takes place if the frequency is below the threshold frequency. The same relation can be written in the form of wavelength. As you know the relation, C is equal to nu lambda. So nu is equal to C upon lambda. So this relation can be written as 1 upon lambda minus 1 upon lambda naught, where lambda naught is called cutoff wavelength. No emission, no photoelectric emission takes place if the wavelength is more than lambda. Means if a substance gives out the electron for green color, then it will not give the electrons, photoelectrons for the red color, orange color. Okay. Now the verification of the laws of photoelectric emission. First law, that is, if the frequency mu is lesser than mu naught, then the kinetic energy of the photoelectron is negative, and which is not possible. So photoelectric emission takes place only when frequency is greater than the certain fixed value called threshold frequency. Secondly, the one photon emits one electron. So the number of photoelectrons emitted increases with the increase in the number of photons. Increase in number of photons means the increase in the intensity of the incident light. Third, that is the energy of the photoelectron is directly proportional to the frequency. Higher is the frequency, more will be the energy. It shows that the kinetic energy of the photoelectron is directly proportional to the frequency of the incident light. Last point, as the photoelectric emission is due to the collision between the photon and the electron. So there is no time lag between the collision, between the incident, the photon collide and the electron emitted. So the process is instantaneous process and the delay is only of 10 to the power minus 8 seconds. Thank you.